Okay, thank you everyone. Sorry, we ran into a bit of technical difficulties getting our presentation. But yeah, thank you for attending. My name is Corey, and this is Daniel. We'll be presenting to you our fourth year design project for nanotechnology engineering. And our design project is printing circuit boards using sintering methods.
Okay, so I'd like to go over the presentation overview just to start off. We'll begin with an introduction, just so that you guys are aware of the industry, what PCBs are, and some of our technologies. Then we'll talk about the problem, which is a problem that's very dear to both me and Corey, something that we experienced, and probably many of you have experienced as well. Then we'll go into a little bit of design, just some of the methodologies, some of the thoughts that went into producing this. Then there's a little bit of analysis and validation of our design, followed by like a summary of the final solution. Then we'll talk a little bit about some conclusions, and we'll finally end with a bit of a question and answer session.
Okay, so before I dive right in, I just want to answer the question is, what is a PCB? So a PCB is a printed circuit board, and it's basically used in any sort of electronic device that's commercially available today, from your smartphone, from this laptop to that projector. It all contains some components of a PCB. And basically a PCB just has conductive lines to connect the parts of different electronic devices or components. It's basically a way for the electronic devices to communicate with each other, either through signals or voltage or whatever. And basically, since these types of PCB is used in every single electronic device, it's very, very important and vital to all of us. And the electronics industry in 2013 is a $60 billion industry.
So the problem at hand, throughout school and even our co-op terms as well, we've run into this problem of creating a prototype PCB. It's all fine, we've done the testing with the breadboard, we've set it up, and we've designed our PCB using CAD software. And now we have to actually get the prototype board. The biggest problem here is that it's very, very time consuming to get the prototype board. First, being college students, we didn't have too much money. We would have to send the board overseas, which would take anywhere between 5 to 30 days to produce and mail back to us. If we were to do it locally, somewhere within Canada, it would still take around 5 to 10 days. And that's only if there was absolutely no errors with it, if there was no defects and everything was working properly. If it wasn't, then we'd have to do an additional order, which would double the time. So it could take maybe like a week to 2 months just to receive our PCB. This process of generating or creating PCBs is actually optimized for bulk orders. So it's very cheap for bulk orders and very efficient, but for prototyping purposes, we found that it was very inefficient.
So when designing our actual PCB, we and the device we wanted to create these PCBs, we thought of ourselves as the customers, because mainly we want to use a device that would allow us to create PCBs quickly and allow us to iterate on our designs much more rapidly than is currently available. So for us, the biggest concern was time. We wanted to have a short fabrication time from batch to batch, so we can have a faster design iteration. Another one was cost. And by cost, I want low cost for each individual PCB. So, for example, if you go to a manufacturer and ask for one PCB, the cost for one PCB is quite similar from 1 to 2 to 3. So there's a very high initial fixed cost. We want to try and minimize that. For the properties of the PCB we would produce, they would have to be good, durable, conductive PCBs, and it would also need to integrate with some of the existing design tools such as CAD software.
So the proposal, after looking at a couple technologies, we decided to go with selective laser sintering. And Corey will talk a little bit more about that afterwards. But the general idea is that we wanted to have a powdered alloy base on top of our substrate, a cheap substrate with high melting point so that we could sinter onto it. And we wanted either the laser or the base to be controllable so that we could trace out the tracks that we needed. Then we would use sintering to actually create the tracks, and the loose powder bed, the powder that was not sintered would just brush off afterwards.
So before we dive in too deeply into our design, I just want to talk to you about sintering and give you a very brief overview. So for a normal sintering process, what you would do is get a powder bed of either metal or ceramic powders, evenly distributed upon your substrate, shine a laser which will then heat up the powder and allow sintering to occur, and then the rest of the powder that's unsintered will be brushed off and be excess. What's really important here is that we make sure that the powder bed material absorbs the actual wavelength of the laser, so we need to optimize that correctly, and that the laser itself would output the correct power required for sintering to occur. Sintering is different from melting, and melting is you actually physically change it from a solid to a liquid phase, while a sintering is more of you're promoting diffusion between the atomic boundaries and the grain boundaries in order to make it more of a what's called solid mass. If you think about like 2 or 3 ice cubes in a glass of water that's combined into one ice cube, that's more closely aligned to a sintering process.
So initially, this is what our proposed design would look like. We have kind of a box surrounding the whole system just for safety measures, since we are dealing with powder and a high power laser. You can see that there is a substrate at the bottom with a small powder bed on top. A blue laser shines down from the top because we found that the absorption wavelength of silver is around that range between 300 to 500 nanometers. And then at the bottom, we also have motors that would control the base and move it corresponding to whatever PCB design that we had.
So going from a much more high-level design to a bit more detailed, we picked out the laser wavelength that would correspond, as Daniel said, which was approximately 445 nanometers, which was the closest we could find in commercially available cheap lasers. Power outage, which would come to approximately 2 watts, which we theoretically determined would be efficient to reach sintering. And the powder itself was a mix of silver micropowder and a bit of lead solder to help lubricate the layers. And then finally, we determined a feed rate of 10 millimeters per second and a spot size of 0.5 millimeters. And these are all mainly theoretical calculations that we did.
So some of the trade-offs that we faced. Obviously, we've related all of the trade-offs to cost. And here, I want to talk a bit about power first. So here, the laser, we actually ran it continuously, but we do know that like a lot of lasers are pulsed, especially when it comes to sintering, and that would have provided a better resolution, but we would have needed to get a much better laser to use that method. So we decided to just run it continuously. The other 3 on top talks a little bit about the silver powder. The reason we chose a mixture of silver powder mixed with a little bit of lead solder here, we needed conductivity to be similar to current copper used in PCBs, and also the oxide of the metal would also have to be conductive as well. In terms of toxicity, we use silver because it's non-toxic. It may be harmful if swallowed, but like people won't be ingesting the silver. It can be handled and it can just be washed off if accidentally touched. We are dealing with microparticles here, just to clarify. And then finally, the durability talks more about the substrate and the powder as well. We wanted the substrate to be durable, it wouldn't fall apart, even though it is just prototyping. And we also wanted the tracks to be robust as well.
Now, while actually working with the prototype and actually using it to actually create a product, we ran into a few challenges and limitations. Firstly, one we correctly predicted but also found it very difficult to work with was adhesion to the substrate. It's quite difficult to adhere the silver and the lead solder appropriately to our substrate, which was glass and fiberglass. And that was something that took us a lot of trial and error in figuring out what was a good composition and a correct way to have it so it doesn't easily fall off to the substrate. Another thing was the laser focusing. As the height of the substrates, or as the height of the powder bed wasn't perfectly uniform in our prototype and in our demonstration, it was difficult to correctly focus the laser perfectly so that everything would reach the correct temperatures for sintering. And safety is also a big concern for us. We would all have to be wearing safety glasses while using our prototype and manually manning it, and that was a big design limitation on our part. There was also the problems of resolution and multi-layered. Previously, we theoretically determined that the spot size of the laser was approximately 0.5 millimeters, but unfortunately, as we're using a heat-based process, the powder composition, the powder density, and the height of the powder all determines the resolution of the actual final printed circuit board, and it turned out to be more closer to 3 millimeters than 0.5 millimeters. Finally, as you may know, most circuit boards are multi-layered, and our current process does not allow for a multi-layered process. In order for it to do so, we would need to attach a drill to our prototype and use it to actually drill down and create the through holes for a multi-layered circuit board.
So I'd like to showcase our final solution. We're also outside group 24, so be sure to check out our booth if you already haven't. From the picture on the left, it's just a full picture of our completed device. We have wooden shielding around all of the sides except for the front so that the operator, wearing safety glasses of course, can man the system. Then we have on the right image here is a glass slide with our substrate sintered onto it. Actually, if you see, the left side has been sintered and the right side is just what the powder bed looks like in its original state. There's a little loonie in the corner just to show the size comparison of like the resolution of our sintering. And yeah, be sure to come check it out outside.
To validate that this sintered material was actually conductive and actually could be used, we used a 4-point probe test to see if it actually worked, and the resistance of the sample itself was approximately 0.126 ohms. There was actually quite a bit of variation due to it being almost like a pseudo powder. So depending on where we actually use the probes, the resistance would change, but we determined it was still under the order of magnitude of silver itself.
We also conducted further validation by running a chunk of our sample under the SEM. The two images are the same, they're just at different magnification. The one on the left here is 800 times, and the one on the right is about 1500 times. What we noticed was that the silver particles did aggregate. You see a big chunk here, and we wanted to check the heat profile of the sintered powder. So we noticed that towards the center, obviously there was more aggregation, and off to the side, because of the properties and the behavior of heat, well, we noticed that there was less aggregation. So this kind of ties in with how Corey mentioned that depending on the location, the conductivity varied.
So just from some concluding remarks, we created a prototype a prototyping tool for PCBs. It validated our conductivity tests and showed acceptable surface adhesion, it wouldn't easily come off and it would be difficult to brush off. And also that this type of technology could be also used for transparent circuits and for multi-layer PCBs after some modifications to the prototype. Yeah.
Yeah. Well, one thing I wanted to add is that also flexible electronics is becoming a really big thing, and we feel like this technology could still be used for flexible electronics with some minor alterations. For multi-layer PCBs, the process would be similar, but after the first layer, we would have to drill holes and add another layer of substrate, and then run the same process again. So it would just be an additional step. Yeah, before moving on to the question and answer section, I'd just like to give some acknowledgements. A very special thank you to Andrei Sazonov, who was our consultant since 3B. He gave us a lot of technical guidance and mentorship. We'd like to thank Jen Kogan, who was in charge of materials acquisition and worked a lot to coordinate all of the FYDP groups. Hani Aziz was the instructor and advisor as well. He helped a lot with the organization of the FYDP. We have some thanks to Neil McManus and John Sad, who helped us with both the 4-point probe and the SEM validation. And so they were our technical support. And finally, UW NRG for letting us use their lab equipment. And we'd like to thank you guys as well for listening to our presentation. And now I will open up the floor for any questions that you may have.
One question is, you didn't show what you created, right? The picture you show is very colorful. I didn't see what exactly the structure you actually printed. Did you print dots, lines?
So I'll let Daniel handle that once we get back to the slide.
Yeah, so, sorry. I'll just go back to the slide. Yeah, so the slide here is just a line along the far edge. Like you mentioned, it's just a line that has been sintered.
So as you can see here, there's a line here where it's hard to see on the projector itself, but if you see the actual demo, the morphology of this line right here is much different than all the powdery bits here that have a lot of like grain boundaries and are not very aggregated, while here it's almost all one solid chunk.
Right, so for this presentation we showed just a single line of sintered powder. At our booth we do have 2 other samples that you can come take a look at as well. We traced like a U shape and also another single strain line.
This is huge, right? This
Uh,
line is very big.
Yeah. So theoretically, we wanted our resolution. Well, we calculated our spot size to be 0.5 millimeters. But when we actually ran the test, we thought it was about 3, maybe at best 3 millimeters for a resolution.
Another thing for PCB printing is that not only you have to print conductive material, you have to print insulating layers. How do you address that in your application?
So we didn't get the time to properly print the insulating layer, but the insulating layer printing could be done using the same process, as SLS is very much used for ceramics as well.
This wooden setup, how safe it is, you think?
Yeah. So as mentioned, safety was a concern. Also with the laser, we did find that if we were to continue with another prototype, we would need a much better shielding. And the obvious next step would be to automate the base moving so that we wouldn't need someone manning the station and wearing protective gear. So if we could just have a completely closed system with printing the board,
So
then that
where
would
do you
be safe.
guys set this up in the lab?
Yeah.
Was this supervised and approved for safety?
This was done under fume hood, and there was no major concerns as long as everyone was wearing safety glasses.
When you said that you were planning to use, like this application could be applied in printed electronics.
Mhm.
Now your laser is probably heating up to the Tedium amount, right?
Sorry?
The laser is heating up to the Tedium's amount.
Yeah.
Mhm.
That's how you're getting sintering.
Mhm.
Right.
How about the normally printed electronics is not a plastic substrates.
So actually normal printed electronics is on FR4, which is on very heat resistant glass, on fiberglass. And basically we would use the same approach.
Have you tried it or no?
We did not get a chance to get it. Our shipment got delayed for FR4, so we just used cover slides instead. Also, there was also another requirement with FR4 that it needed to be, we need to get the uncoated version because if there was a significant color layer, it may be absorbed too much into the FR4. But we did not get to experimentally test either one.
My next question is why your resolutions are so poor, 3 millimeters or so. Even 500 microns is very poor.
Mhm.
Why wouldn't you do what hobbyists have been doing forever, which is print the printed circuit board on transparency and use copper or sulfate and just etch copper?
So the initial inspiration behind this project was with how 3D printing is blowing up, and they're doing like rapid prototyping of like physical models using 3D printing, and we wanted to achieve something similar to that could be high speed and low cost, and so that's how we got started in this direction, and then we just decided to push through with it.
But yes, in order for it to be more commercially viable, we definitely need to work on the resolution and the other components of the device.
All right. Thank you very much.
Thank you.
Thank you.